What if our straight line path is parallel to an axis, the x-axis and y-axis on the complex or the organ plane? How do we parameterize or provide the parametric form of your function to be included in the integral form? We know that the integral along your path C of your function z dz is equivalent to the integral of your function of z of t times the derivative of z of t with respect to dt from a to b. In the previous video, we're able to provide the parametric form or the formula in order for us to identify the z of t, which would later on allow us to also identify its first derivative, which needs to be included in this form so that we can actually solve for that, together with your a and b coefficients as well. Now, what if the line segment is parallel to an axis? So it's different from the previous one. Let's also separate this into two forms. Let us have here horizontal line. Okay? Horizontal line segment. Because for horizontal line segment, there is this different form for it than the vertical line. So for horizontal line segment, we know that for our organ plane, okay, let's say for example here, let me illustrate that here. Horizontal line is somewhat like this. It is parallel to your y-axis, right? And as therefore we know that this equation is y equal to a certain, let's say k, which is the value of y where this line intersects with. Okay? So the parametric form or the parameterization of the horizontal line is in this manner. Your z of t is just basically t plus I k. That is its form. Where your k is actually the intersection, again, of your y or the value of your y along the axis where it intersects the y-axis. Okay? So this is its form. But your t is between a and b. The identification of a and b depends on the real part. Because when you look into this horizontal line, the y value doesn't change. And we know that for the certain form of your complex function x plus iy, okay, the y is actually part of your imaginary, or together with its imaginary unit, right? So the real part is your x. So your x changes its value as you go along this horizontal line segment, because your x here also changes its value. So your t is actually the values on your real part of your given functions. Let us have an illustration for this. So say for example, from your z sub 1, which is 1 plus 2i, and your z sub 2, which is of course 4 plus 2i. Take note that this part did not change because obviously it's horizontal. We know that here our y is 2 because this is the y value iy. Okay? Our t here is between the values of your real part, which is 1 to 4. So it's actually between here 1 to 4. This is your a and that is your b. Okay? So with this now, the parametric form of that is obviously equivalent to your z of t, which is your t, okay, still t at this point, and you have here plus 2i, where t starts from 1 to 4. Okay, so that is actually your z of t. We need to plug in here, and of course its first derivative with respect to t, treating all terms without t as constant, the derivative of that is actually 1, plus the derivative of this with respect to t is 0, will give us 1. This is your z prime of t. So this is what you're going to plug in here. And this value for your z of t will be substituted to whatever your function is. And then your a and b again are the values integrated by this changing values of your real part. That's for the horizontal line segment. I would like you to focus here. This is actually its form. Now, what if we have a vertical line segment? A vertical line segment. We know in our plane, okay, this is our plane. If it's vertical, the value that will not change is actually the x value, right? It's the x value that will not change. But all the values on your y will actually change. So it would actually differ from one location to the other. So when we're talking about a vertical line path, its actual form, okay, take note for this, don't forget that as we have our z here earlier, this is actually, let's say, let's use also k. This is actually x is equal to k, unlike earlier it was y, okay? So its parametric form is equivalent to k as the value of your x, plus it is now your y that would change its value. Compare the two. Earlier, your real part is t, the value that will change along the horizontal line segment, but your k would be still the same, that's your y. Here, it's now the k, or your real part, which stands for x, that will not change, as it's the value all the time as we move along that vertical line path, and it's your y here, this form here, that will change the value of t. And your t is again between a and b. The value of your a and b will now be different from this because earlier it was on the real part. So say for example, we have here from z, which is actually, or z sub 1, which is actually 3, to z sub 2, which is equivalent as 3 plus 4i. Okay, so your k, this is your k, right? Your k did not change, right? But your t here is actually 4, but this is equivalent to plus 0 I, of course. So it starts with 0 to 4. This is your t, 0 to 4. This would be your a value, and that would be your b value. So in short, your z of t indicated by your k plus it. Your k is actually indicated as your 3 in this case, 3. So you have 3. Let's remove this one here. Plus your I t. Okay, it, where your t starts from 0 to 4, because it's the value that did not that will change here. Okay, plus 0 to 4. And of course, if we're going to take its first derivative, you will have here with respect to t, so all the other terms without t will be treated as constant. Derivative of your 3 is 0. Derivative of this with respect to t is actually I. This is equivalent to I. This is what you're going to plug in together with this form in our formula for the complex integral of your function along path C, in order for you to solve for the integral of that for the vertical lines. We will have also other examples later on, okay, to illustrate them. But obviously, this is how it works. For the vertical, horizontal line, it's in this form, this one here. And for the vertical line, it's in this form as well. The identification of A and B differs from one another because for the horizontal line, your A and B is the change in your real part. But for vertical line, your A and B is the change on the numerical coefficient of your imaginary part, 0 to 4. Very important because they are not the same, and obviously your A and B coefficients are important in your integral here. This is how we parameterize straight line segment parallel to an axis. Thank you very much for watching.